Aerodynamic forces.
What's love got to do with it?
What's lift got to do with aerodynamic forces? Well, if you're designing an airplane, you need to know how much lift it can provide given its weight. And oftentimes, this is determined using a coefficient of lift. And we have a certain angle of attack down here. So, coefficient of lift, angle of attack on the bottom. We figured this out by using a wind tunnel. And so, this Cessna, the red dots here, shows a coefficient of lift that's constantly increasing until we get to about 15 ish degrees, and then it begins to lose some lift, and then right here is where it begins to stall out. Whereas the BAC Lightning has a swept back wing profile. It continues to gain in coefficient of lift really all the way up to about 30 degrees. So depending on the wing style, you can have a higher coefficient of lift before you get to your stall angle. But a lot of things determine coefficient of lift, and we're going to take a look at that with this presentation. So first, do not write this stuff down. Just take a look. So let's take a look at this graph, which is coefficient of lift and coefficient of drag, all on the left-hand side. It says CD, but it's actually CD and CL. They use the same sort of scale. And then we have angle of attack on the bottom. Let's first try to make some sense of this. Your coefficient of lift line, this diagonal line here, this line is constantly increasing as your angle of attack increases. You have a larger coefficient of lift, which helps determine lift. And that drops once you get to this particular aircraft wing, begins to stall right around this 18, 19, 20 degrees. So coefficient of lift quickly drops off. Well, let's look at coefficient of drag. Your coefficient of drag slowly increases and then increases more and more rapidly. So as you have an airfoil, when you start to increase your pitch, then your drag increases because you have more wind attacking this large surface, and you're going to have a larger drag value as this angle of attack continues to increase. So if you take lift divided by drag, which gives you efficiency in lift to drag ratio, then you have the most efficient lift to drag ratio at a pretty low angle, about 6 degrees. You have the best lift per drag. And so if we looked at this, that actually is the greatest difference between these two values. Your lift to drag is the greatest, where lift is higher. So that's why that's the most efficient here. And then it begins to drop off until we stall here. So that's really all this graph is trying to show. It just gives you a representation of lift and drag. Now we're going to have to start writing a few things down. Here's your lift equation. So you have coefficient of lift, which is CL. That's determined experimentally. Again, that's done using a wind tunnel. It's a combination of several factors. You have shape, angle of attack, and also depends on these things. So go ahead and jot this down in your engineering notebook. And guess what? You're going to also put this in your aerospace calculator. Yeah! Because we want this thing to be a really easy calculation to do later on. So coefficient of lift equals 2 times the lift, and lift that we need is actually going to be equal to or just greater than or equal to the weight of the airplane, because lift is up, weight is down. So whatever the weight is down, we need the lift to be greater than that value. Area wing density, area is in square meters. That really matters. Make sure you have units. Density is kilograms per cubic meter. Density is sort of slanted P. You got to be really careful that you don't write that as a P, because that is pressure. So that's going to be something that is very, very, very confusing later on. Make it a really slanted thing, or you can just use a different letter, or just write the word density. And then V is velocity in meters per second. Units really, really matter. So we calculate density, and I now write the word density. I don't use that little slanted P. Here is sort of a italicized P. The character is a rho, but I'm going to write the word density. I suggest you do the same. Density equals pressure divided by this value right here, and that's how we get air density. And here's another calculation for this is the actual equation. It has the symbol, and then we have units. I don't need you to write down the units for it. This bottom one here is probably the most efficient way to do that. So make sure you have that in your notes, and you're also going to put that in your spreadsheet calculator. Yeah. So if you have not, pause this to add those things to your spreadsheet calculator. Do that right now. Call me over to you if you need a little bit of help, and I will happily help you create that. Once you've created it, then I want you to write down the things that you know from this problem in your engineering notebook. And like we know standard pressure, we know the takeoff speed, and so on. But guess what? This is not in the correct units. It has to be in, as we look back here, meters per second. So you need to make sure that you have everything converted into correct units. You could add those little nuggets into your spreadsheet calculator if you want to add some little conversions. So you can just type it in kilometers per hour, or you can just Google 102 kilometers per hour to meters per second. That would be a really easy way to solve that problem. You're gonna have to figure out, make sure the areas are all in the same units and the weight. So why do we have weight? Because weight has to be equal to lift in order for it to just barely take off. That is a minimum takeoff when the weight is equal to the lift. So I know it says weight, but that is what you're going to put in for your L value for lift. So go ahead at this point and pause this and see what you get for your answer. Pause. All right, so we converted mass into weight, and this would just be using the formula how you would do it. You do kilograms times gravity, so we get 10,359 newtons. You can Google that conversion, 1,056 kilograms into newtons. And velocity we had to convert, and we get 28.3 meters per second. And then air density, if we plug that into our spreadsheet calculator, we're going to get 1.196. So you can check all those values in your spreadsheet calculator, make sure those were all correct. And then coefficient of lift, we plug in all the values, boom, 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 and you get 1.19. So 1.19 doesn't necessarily mean a whole lot to you. It's just a value. But if you went back into that other graph, then you could plot that as a point. And then you could experimentally plot a whole bunch of different points. And then you could get sort of a curve that would give you a better representation and understanding of how that wing works. Let's talk really quick about boundary layers. We learned a little bit about this, or at least it was mentioned in the video about how wings generate lift. And boundary layer is just where fluid molecules will stick to the object's surface. This creates a boundary layer of slower moving fluid, and boundary layer is also crucial to wing performance because you have a slower velocity here. So that's going to add a little bit of extra friction or resistance around this. We're not going to get into all the things that that does, but you just need to know that that is a reality. The air does not flow freely right next to the top or right next to the bottom. We have this thing called boundary layer. So if you get into aerospace engineering, you'll learn a whole lot more about that. What happens because of that is this thing called turbulent flow right here. Laminar flow is when everything equally moves smooth, but once we have a variation in velocity, we get a little bit of turbulent flow. You can see there's no pencil mark here, so it's not something that I need you to note down. I'm just giving you a little bit more information here. So we want the airflow to remain smooth until we get this critical airflow velocity, but it does end up slowing down and it causes a little bit of turbulence, which can affect the performance of the wing. So let's take a look now at angle of attack all the way up to the stall angle. As your airflow hits this, you get a increase, relatively linear increase in your lift versus angle of attack until you hit the stall angle. And that's where we get the separation because of the kata condition, where it does not want to turn sharp corners. And then we get this turbulent flow, and then we lose a lot of this turning of air. So we all of a sudden don't get nearly as much lift because we are losing all this turning of air on the top edge of this airfoil here. So let's try a practice problem at this point. Now you're going to have to use this graph right down here to figure out what the coefficient of lift is. So question, what is the relationship between coefficient of lift and angle of attack? Well, if you have an angle of attack of 8 degrees, then your coefficient of lift is, according to this graph, 0.8. So you can plug in 0.8 right here, and you can plug in all the other values. Now, this says if you're flying this aircraft and it weighs 52,500 pounds, so we have to convert that to newtons. That's going to be our lift value. Then you want to maintain an altitude of 30,000 feet. You may need that in meters if you're going to figure out air density. And I put a little d to represent density here. And you're cruising at 400 knots. I believe we have to have as meters per second. So you have to convert all these things. And then we have an area of a wing in 1,140 square feet, which is supposed to be square meters. Yes, I'm a horrible person because I make you convert all of these things. So make sure that you do that before you try to plug these things in, or your numbers are not going to work out at all. So you're going to have to convert all those things. Well, you need to figure out what the angle of attack is, but you're solving for CL. So once you solve it, you're going to get a value here. You go over, translate that to what the angle of attack is, and that's how you'll solve this problem. So at this point, you should pause it and you should try to solve this on your own. If you have any hard times with this, please bring me over and I will help you. Pause. All right, I'm going to click through this and you can compare it with what you got on your values. So I have all my conversions here, and then we put those numbers in and we get a density here as well. We're plugging values in. We get 0.222. So 0.222, if you're looking at a CL value of 0.22, it's just right about here. So I'm getting somewhere in here, which is close to about 1 degree. So it's an approximation of about 1 degree because 0.2 is just less than halfway. And so we're right around here. So I would say about 1 degree. That's why it's an approximate thing here.